Thank you to the organizers for inviting me. Yes, I changed the title and I apologize for this because I did exactly the opposite of what you described in your introduction. Instead of taking a more general point of view, I decided to focus on something something smaller. The reason is that if I had spoken of the same subject as my contribution to the book, I think first that it would take too much time, and also that there are many specialists of quantum mechanics in this room, and they basically know everything I could say. So I decided to focus more on a specific point, and I chose one interpretation because it's kind of amusing because it takes contribution for different interpretation of quantum mechanics. So I'm going to speak mostly of non-standard quantum mechanics. And after all, that's okay because during all my life, I spoke about the standard quantum mechanics. So from time to time, it's fun to make a little change. Okay, so this is the organization of my talk. First of all, I will just use one transparency to say something general of quantum mechanics, which is, as you know, a wonderful theory, but still difficult, delicate to really understand. Then I will discuss three non-standard points of view. DBB, which is the Broglie-Bohm theory, which probably all know. The dynamical collapse theories, and Penrose's suggestion in 1996. And then I will discuss a model combining the 3 points of view. I will probably skip point 4 since we are late, so I will try to save time. First of all, as a general introduction, you all know that quantum mechanics is an absolutely fantastic theory, and not only intellectually. I mean, it has a enormous number of applications. For instance, it is behind all the solid-state physics, which means that it's also behind transistors, telecommunications, computer, internet, etc. It is also behind lasers, atomic clocks, then navigation, GPS, and there are many examples. In a sense, this room is full of objects that have been invented with the help of the understanding of quantum mechanics. But although it has strange, maybe even very strange features, I could speak for 1 hour about this, but I would just try to summarize it in one sentence. The major difficulty, according to me, is that its dynamics is based on linear differential equations. And this equation seems to predict sometimes the appearance of what I called after Tony Leggett QSMDS, that is quantum superpositions of macroscopically distant states. And we never observe this QSMDS. So this is a difficulty. And one case where this situation happens, for instance, is every time you do a quantum measurement experiment. In other words, how a single result can emerge when you do a single experiment, single quantum measurement, is not explained by standard quantum mechanics. You need to introduce some postulate to explain it. And this is often called the measurement problem. But after all, what should we accept this situation? Why should the physical theory not be able to describe in detail what happens every time you do one experiment, which is the case, always the case in the lab. So, of course, people have developed, scientists have developed strategies to overcome the difficulties and developed philosophies or epistemological consideration to explain why the theory cannot or even should not do better than what it does. The most famous possibility is the Bohr-Copenhagen interpretation, which assumes a Heisenberg cut, a split between the world of measurement apparatuses, which are macroscopic, and which more importantly can be described in ordinary human language, and the quantum world, which cannot. Bohr even said something rather strong about this. He said, there is no quantum concept. There is nothing to say in itself about the macroscopic world. As you probably know, this interpretation has many variants. Many authors have proposed to express similar ideas with different semantics and to reconstruct quantum mechanics in different ways. I cannot say more about this because of the lack of time. Von Neumann suppresses the problem more radically without any philosophical consideration. He just introduces a postulate, the quantum projection postulates, which modifies the dynamics. The usual dynamics stops at some point and is replaced by this projection. This is the most frequently a version of quantum mechanics that is taught to students. Or the last possibility is to accept to change something, to do something. Since there is a problem, after all, it may be useful to try to see if we can change the theory and, of course, change it in a reasonable way so that it won't be contradictory with all the known facts that have been checked with the usual theory. So this is what I'm going to discuss today. So now I will recall three non-standard points of view: DBB, de Broglie-Bohm. So if you have any interacting particles described in standard quantum mechanics by the Schrödinger wave function psi, psi propagates in the configuration space, which has 3n dimensions plus time. And DBB introduces one additional variable Q in configuration space, which is the Bohmian position of the system, and which is guided by the phase gradient of psi at any time. The standard view is to consider that the components of Q define the n individual positions of the particles, which are considered as the real positions of the particles. And from this, you can build an ontology. But I want to mention that another important, in my eyes, property of the DBB theory is something else, is that any subset of particles can be described at any time by a single wave function, which is called the conditional wave function. And this is not true in quantum mechanics. In quantum mechanics, when systems are entangled, as Anna described before, each subsystem gets a several wave function or density operator, if you like. In DBB, even when a particle is entangled with the others, it constantly keeps a single wave function, propagating in ordinary space. And needless to say, in a single realization of the experiment, the wave function undergoes the fundamental projection postulate. Now, a second classical but non-standard approach to quantum mechanics is the dynamic collapse theories, where you modify the Schrödinger equation to introduce a collapse mechanism. The most famous versions of it are GRW, Girardi, Rimini, Weber, in 1986, CSL, introduced by Phil Pearl in 1989, or a version related the collapse to gravity by Joshi in 1989, and many more references since. Anyway, the additional variable in this case is a random field that moleculizes wave functions spatially. In GRW, the process is sudden. It's a hit that suddenly projects a wave function. In CSL, it is continuous and described by the Wiener process. Durshi introduces the classical noise field with a spatial resolution related to gravitation. Anyway, what is important to remember is that all these theories require the introduction of two-dimensional parameters. You have to introduce one length, localization length A, and a localization rate lambda. My 4 lambda has fallen down by one line for some reason, because we're in the basement. These theories make predictions that may differ from standard quantum mechanics, which is kind of nice because it can simulate experiments. And actually, around the world, there are something like 5 or 6 experiments trying to see the effect of this dynamical collapse. There is a large literature on the subject, which I'm not going to review. And finally, the third non-standard idea I would like to discuss is Penrose's 1996 suggestion. He remarks that if a massive object is put in a superposition of states in different regions of space, I have my ball of lead here and there, and was square root of these two possibilities, as Alan discussed. General relativity predicts that one obtains superposition of different space-times, which is not so easy to conceive. And then the notion of time translation is ill-defined, and the energy has an uncertainty. I have given below a few references to Penrose's articles. So now comes his suggestion. He says when there is an uncertainty of energy delta E, it's very natural to use the time energy uncertainty relation and to introduce a term which is h bar over delta E. And he postulates that each time this coherent superposition of space-times occurs, it is projected onto one of the configurations in a time tau. So the end result is just equivalent to the standard Feynman postulate. Penrose proposes no mechanism for this. This is just a general idea, but there are no equations except the time-energy uncertainty relation to explain why this is the case. Now I'm going to discuss a model combining the three ideas. I have no idea what everything is. I will discuss a model which is, in a sense, very naive, but also I'm using because it works pretty well in terms of predictions. So we assume now that the source of gravity is not the density of matter predicted by the Schrödinger equation, psi square, but that it is the Bohmian positions, which are, in a sense, a classical position. They are still driven by the quantum state vector. This is the dBB guiding equation. So in this case, gravity remains a classical field. We don't have these superpositions of different space-times. The space-time is classical. It's a frame inside which all the other quantum interactions propagate. This idea is not new. It has been proposed by Brossel, for instance, in a paper in 2019. Patrick Peter and co-workers in the context of astrophysics, cosmology, or Antoine Tilloy in a more recent paper. Conversely, of course, we expect that gravity will act on the state vector. So the idea I propose is to write this interaction. This is on the next slide. And as we will see, to add, just by hand, I mean, without any, to postulate that the gravitational Newton constant gets a small imaginary part. So here are the only equations I will show, and the one below I don't even know. So I don't even need. The Hamiltonian of the system is the sum of H ant, which is the internal Hamiltonian, with the kinetic energy interaction between the particle. This is the Hamiltonian that we all use when we do atomic or molecular physics, plus Hg, which is the gravitational Hamiltonian. So the source of the gravitation is the Bohmian position, as said. It results in a density of matter in space, which is this function ng. So I put it in this integral. So this is the classical gravitational potential at any point r. I multiply it by the quantum operator, giving the density of the particles, and I get. I also introduce the Newton constant and the mass. For instance, I suppose the G is 1, and this is the very standard gravitational Hamiltonian. So if G equals 1, you get something which is very standard, except that you have assumed that the source of gravitation is the Bohmian position. You don't use the so-called Newton-Schrödinger equation, where the source of gravitation is the quantum density expressed as a function of psi. And this equation has problems, for instance, with superluminal signaling. This one doesn't. So now I do something else, and I add a little I epsilon to J. So you may be horrified because this changes the Hamiltonian into an operator which is no longer Hermitian, which means that a few things have to be changed in the formalism, but this is not a real difficulty. You can write the equation for the normalized wave functions, which is given below. The only point I want to emphasize is that this model introduces nonlinearity because the Bohmian positions are given by the wave function, and they act on psi. So we have broken the linearity of quantum mechanics, and we have to do that because if we don't, we will never be able to explain why a single experiment provides a single result. This is what the model predicts. First of all, we have to consider macroscopic systems, typically hydrogen atom. In a hydrogen atom, of course, the proton and the electron interact not only by the Coulomb potential, but there is also a small gravitational interaction. But we always ignore the latter because the ratio between the two constants of the two fields is enormous. It's written here, it's of the order of 10 to the 39 or 40. So it's very safe to ignore gravity in the hydrogen atom. And from this remark, you can understand that in any macroscopic systems, what I propose to change with my little epsilon may be 10 to the minus 3, so we will go to the 10 to the minus 41, and there is no risk to see any perturbating effect in molecular, atomic physics, and so on. So this may look a little, even a little bit discouraging, because it gives you the feeling that you will never predict anything, because this number is too large. But it's not the case. Suppose you are doing an experiment, a quantum measurement experiment, and this blue arrow symbolizes the pointer of the measurement apparatus. So initially it sits nicely there at 0 and it says nothing, but when the measurement is completed, if you apply the Schrödinger equation, the pointer ends up in a superposition of two states indicating two different results, a Schrödinger cat if you like. Okay? Now what happens to the Bohmian positions? Let's consider the Bohmian position of the particle in the tip of the pointer, for instance. So they have to follow the wave function. This is the effect of the guiding equation, quantum equilibrium condition, if you like. So they have to be either here or there. But one important point is that they cannot spread among the two positions. This is because state vector is a superposition of all particles being here and all particles being there. So they have to make a choice, the Bohmian position. They have to go all to one side or to the other side. If you like, this is a consequence of the cohesive forces inside the pointers which drives the wave function. So they have to go either here or there. So you can immediately understand that this will create different gravitational fields, and the difference of energy is of the order of Newton constant multiplied by the square mass of the object you are considering, divided by its size. And now the important remark is that this energy contains the square of the Avogadro number, because this is more or less proportional to the Avogadro number. And then we are saved, because the Avogadro number is large. So you end up 9 orders of magnitude, or 8, I forgot, above the preceding number. So in this case, because you have, if you want, a collective effect between the gravitational effect of all particles in the pointer, you can overcome this large factor and project the state vector in a term which is of the order of this as guessed by the Penrose in his paper. So let me say a few more words about how this collapse occurs. First of all, what happens is standard quantum mechanics. The small quantum system gets entangled with the measurement apparatus, and the entanglement propagates in the measurement apparatus at a speed which can be maybe the speed of sound inside the measurement apparatus, and the number of particles will become entangled with the quantum system is larger and larger. Remember that the gravitational energy was of the order of the square of the number of particles taken in the entanglement divided by the size of the object. So if you take an object at constant density as a function of its size, the collapse time changes like 1 over L to the 5th power. So you have a process where the time constant constantly decreases and decreases like the 5th power of L, which is the size of the object, which itself propagates linearly in time. So what you create is a system process which is almost instantaneous. So at some point you have a very sudden, brittle projection of the state vector, and you reproduce the fundamental collapse almost perfectly well. But intellectually, it's satisfactory because you can calculate what happens how many particles have to be involved in the process and so on. So it gives it gives a big background to the fundamental postulates. So of course you can see that this model is very, very naive. It's artificial to put an imaginary part in the Newton constant, and maybe even more seriously, it's not even relativistic. I mean, it's based on the DBB theory and on the Schrödinger equation. So any field theorist will find this model to be too naive to be even considered. So the only merit of this kind of model, I think, is not to say that I have discovered what happens in physics. It's just to show it's possible to do such things. It doesn't contradict any known fact, and it's not, I mean, there is no impossibility theorem forbidding this kind of theory. So as I said, the particles are not localized independently, but by a collective effect, which is a big difference with the standard GRW and CSL collapse theories. And although it has a very simple dynamics, I mean, it's much easier to understand than the CSL paper, for instance. It says that the origin, what creates the result of measurement, is not the state of the quantum system at all. I mean, as you have seen, as I said, what projects the whole system, projects the whole entangled psi is what happens inside the measurement apparatus. So what creates the result is something that happens in the measurement apparatus. It doesn't reveal a pre-existent property of the measured system. This is also true in standard DBB theory, by the way. Maybe most importantly, this model introduces no dimensional parameters. So it's different from the usual projection dynamical collapse theories. And there is one parameter epsilon. If you like, you can take it equal to the defined structure constant, and then everything works perfectly well. But of course, this is arbitrary. Now, a final word regarding ontology and philosophy. This model is very neutral. I mean, you can keep the usual DBB point of view and say that what is real is the positions of the particles. If you take this point of view, the only advantage of the model is that you have a psi, a wave function, that constantly follows the observation very well. You don't have this psi ramifying in all directions with all these empty waves that persist in the DBB point of view. Or, if you want to take an opposite point of view, you can say, oh no, what I want to decide is that reality is represented by wave functions. And then you can take this point of view, because as I said, every particle keeps constantly a wave function which follows the observation. So you can come back to the initial hope of Schrödinger in the 1920s, that psi would be the ultimate object to describe reality. Or you can keep both, psi and the Bohmian positions. Okay, I think I will stop here, and thank you for your attention.